Hi viewers, welcome to LMS Solution. Today we are going to see about harmonic mitigation in a grid connected PV system using Shunt active power filter. This is a simulation model we developed for harmonic mitigation in grid connected PV system using Shunt active power filter. This model consists of PV array. The PV array is going to be connected to the inverter via this boost converter. This inverter going to be connected to the point of common coupling via this LCL filter, and then here we have that grid, and here we have shunt active power filter. So here we have non-linear load. The PV array rating is 100.2 kilowatts. Here we are using 47 parallel string, each string having 10 series connected model. Single panel maximum power will be 213.15 watts, and voltage at maximum power point is 29 volt. So this is IV PV characteristics of the considered PV array, and it will be connected to the inverter via this boost converter. That boost converter going to be controlled by means of P into MPPT. So MPPT is receiving two inputs, one is PV voltage, another one is PV current, and output will be reference voltage. The reference voltage going to be compared with the PV voltage and processed via PI controller and compared with the sawtooth waveform, and finally we'll get the pedal impulse. So this pulse is going to be controlled this IGBT to extract the maximum power from the PV array as well as boost the voltage from 290 volt to 700 volt. 700 volt nothing but the DC-link voltage of the inverter. This inverter, three-phase inverter, going to be controlled by means of voltage and current controller. And current controller, here we are using feed forward decoupling control concept. For that we have to use PLL. This is a PLL. The PLL going to be generate omega t, and then we are converting grid voltage and inverter current to DQ0 format by using power transformation. Here we have VDVQ and IDIQ of the three-phase inverter of the PV side, and here we are measuring the DC-link voltage and going to be compared with the reference voltage, and it going to be processed via PA controller. So this controller going to be generate the reference current in the form of ID reference. So this ID reference going to be compared with the ID actual of the PV inverter, and here the IQ reference is 0 because we are sending only real power to the point of common coupling via this inverter from this PV source, and the IQ reference going to be compared with the actual IQ of that PV inverter, and it going to be, that means the error current, right? This error current going to be processed via this PI controller, and then this two PI controller will be generate the control signal, and this portion known as a feed forward decoupling control concept. Here we are applying that feed forward decoupling control concept, and finally we will get this control signal the form of D and Q. Again we have to convert the D and Q into ABC form by using inverse power transformation. So here we will get the three-phase controlled voltage. This three-phase control voltage going to be compared with the triangular wave for generating the pulse for that inverter, three-phase inverter. This pulse going to be control this inverter to maintain the DC link at 700 volt DC link voltage, and whatever power we are generating from PV array, that going to be through via that three-phase inverter to that point of common coupling. And here we have grid voltage is 400 and frequency is 50 Hz, and here we are using non-linear load, that means diode rectifier with RL load, and here we have shunt active power filter. This is a DC link capacitor for shunt active power filter, and it consists of three-phase inverter, coupling inductor, voltage controller, and then compensating current calculation by using PQ control theory, and then here we have hysteresis control as well as PWM control. Here we have to measure the DC link voltage. The DC link voltage going to be compared with reference voltage 700 volt, and it going to be processed via PA control. That PA controller will be generate the power loss component for that PQ control theory, and then here you have to use grid voltage and the load current for generating the compensating current, for that is shunt active power filter. Here we are using PQ control concept by using grid voltage and load voltage. We have to calculate alpha beta 0 voltage and alpha beta 0 current. Based upon that we have to calculate PQ and P0, and then after calculation of this PQ, P0 and I0, so next you have to calculate that mean you have to calculate difference of average power and actual real power. The final power will be going to be subtracted with the power loss component, and finally we will get the real power requirement. Based upon this real power requirement, reactive power requirement, and then P naught, I naught, and then grid voltage. Here we are applying the inverse peaky control theory concept. So here you have to calculate alpha beta 0 component of the voltage. So here you have to calculate alpha beta 0 component of the current, and based upon that, here you are going to calculate the compensating current for that syntactic power filter. So next process after generating that reference current, that reference current will be compared with the syntactic power filter current. The difference between the reference current and the syntactic power filter current, then it can be processed a hysteresis controller. If you want to use hysteresis control, you can use hysteresis control. So here you are using PWM generator. The difference of that reference current and actual current when we process a PWM generator, it going to be generate the pulse for that three-phase inverter of the syntactic power filter. So it going to be control this three-phase inverter for injecting the compensation current now to mitigate the harmonic in the grid current. So this is operation of that grid connected PV system with the syntactic power filter for harmonic mitigation. Now I am going to explain the simulation by not considering the non-linear load and the syntactic power filter. That means PV generating power and sent to the grid, and you have to check the THT of the grid current, and then after that you have to include non-linear load, and then you have to check the THT of the grid current, and finally you have to add syntactic power filter, and then you have to check the THT of the grid current. So you have to see the difference of THT of the grid current for a different mode of operation. Now we are not considering the non-linear load and the syntactic power filter. This is a result of PV power, grid voltage, grid current, and the DC voltage of the inverter. After completion of simulation, we have to check the THT of the grid current. Further, go to workspace and click this one out, and then here you can click scope data 2 and then track here, because the grid current component stored in the scope data 2. After that, go to simulation and go to power GI and tools FFT analysis and click input 2, and then click CMS maximum frequency and click display. So here you can see that when the grid is sending power to the grid, now we are not considering any non-linear load in the system. We are getting almost 3.63% THT. That means it's less than 5% only. And that means it follow that IEEE standard. Now I'm going to include that non-linear load in the system at the point of common coupling. So this non-linear load I'm going to add it here. Now I'm going to simulate the system, and then you have to check the result. We will get the same PV power, grid voltage and DC voltage, but there is some changes in the grid current. That means there will be some distortion in the grid current, because now we have added that non-linear load, right? Because of non-linear load, what happened, right? It draws the reactive power from the grid. Because of that, the reactive power as well as the nature of the grid current will be non-sinusoidal. Now we are going to check the THT of the grid current after adding that non-linear load, and I'm going to refresh this one and click input 2 and then check the THT. Now you can see the THT, right? The THT is around 7.23. It more than 5% is not obey the IEEE standard. Now I'm going to add that the syntactic power filter in the point of common coupling. Now I added the syntactic power filter in the common coupling, point of common coupling, and then I'm going to simulate the result. And then here you have to check the grid current quality, whether after adding that the syntactic power filter, whether THD goes down to less than 5% or it remained at 7%, 7.63% or not, right? We have to check that one, right? Now we added that syntactic power filter in the point of common coupling in order to mitigate the harmonics in the grid current, right? We have to check the result. So after checking the result only, we can justify the result. After completion of this simulation, we will go to check the result of the grid current THT. Again, I'm going to check the THT of the grid current with the syntactic power filter. Now we can see that the THT comes down to 4.85%, right? Now the THT is 4.85%, is less than 5% only. After adding syntactic power filter, so that as syntactic power filter mitigate the harmonic effect in the grid current. That means it eliminate the harmonic component in the grid side current, right? So the syntactic power filter will be eliminate the harmonic effect in the grid current. This is the working of the harmonic mitigation in the grid connected PV system using shunt active power filter. Thanks for watching our videos. Kindly subscribe our channel and also click bell icon for notification about upcoming videos. Thank you. Thank you so much. Bye bye.